Welcome back, friends. My name is Jagmar Ravindran, and I am preparing a series of video about group actions. Now already 6 videos are uploaded. Now we are at 7th video. In this video I'm going to prepare things for Sylow's theorem. Okay, already 6 videos are uploaded. You might want to see to understand this. Okay, let's see. So the preparation, I wanted to prove the Sylow's theorem. The idea is I am following Michael Arden book. You have to go to read about the introduction. So it's kind of inverse to Lagrange's theorem. Okay, so Lagrange's theorem, we know that I have a subgroup of a finite group, then the order of H divides order of G, right? So this is Lagrange's theorem. It says that. Now the question is reversed. Suppose I will give you the divisor. Is there exist subgroup of G such that H equal to D? This is not possible in general. I can give one example. Check these examples. In A4, try to prove there exists no order 6 subgroup. Try to prove. Okay, in A4 order is 12 and 6 divides 12. Okay, fine. In later on, after simplicity, you can understand A5 also having this kind of problem. The order of A5 is 60. There exists no 30 order subgroup. If exists, that must be normal. After proving simplicity, I am just giving for motivation. Now let us see. I want to do preparation, so my notations I am going to fix it. N going to be always the, it means that always a group order. This N always a group order. We are in finite setup always. Maximum p power where p is a prime. This is I am going to fix. Okay, p prime and maximum power I have taken out. What is this meaning? P power alpha divides n, but p power alpha plus 1 does not divide n. This is the idea. So maximum power I have taken out. This is equivalent in the setup. Okay, now under this setup, first lemma I don't wanted to prove very formally this is easy. This is the first lemma. Okay, let n be that integer, positive integer, p power alpha into m fashion, n equal to, and p power alpha divide n. Also this is greater than 1. Okay, that's very important. Then n equal to n choose p power alpha. Take this name, let n, then not here, then p does not divide n. This is a claim. That means what I am doing, I am taking out the maximum power out, then p will not divide this thing. Okay, let's prove this. I am just little bit vaguely prove. This is not very important. What is n choose p power alpha? That is n into n minus 1 into dot n minus p plus 1, like that, divided by 1 into 2 dot p power alpha. So I wanted to prove p does not divide this n. This is a claim. The idea is here. Let's look at one factor here. Okay, one factor looks like n power is some k, right? And the down factor will look like p power alpha minus k. That many things are happening here. Okay, that is equal to m p power alpha minus k. This is p power alpha minus k. Remember that suppose I can take, suppose this k is a multiple of p also. Let's say I can take p power beta, the maximum thing that divides m p power alpha minus k. That implies p power beta will divide p power alpha minus k. Okay, beta less than or equal to alpha. Remember that. Okay, because here the p power per beta maximum I am taking, that means that will also come from here. Okay, so in what we are actually doing, whenever some p power beta divides here some factor, that will divide here p power beta. So each and every factor, all this p will go away, no p will remaining. So in that way p does not divide n. Okay, for more information please refer Algebra by Michael Artin. Okay, now next lemma, the next preparation lemma is this. Okay, let u belongs to power set of G. Okay, for a precise statement you have to refer Michael Artin. Okay, as I said, I don't want to make any replacement for traditional teaching. Okay, let G act on power for alpha like this, okay. This makes perfectly sense because both are group element. Okay, you can check, this is group action. Okay, now fix this. So the step of u, the stabilizer of u, actually my claim, then stabilizer of u, the cardinality of stabilizer of u divides u cardinality, and step of u divides cardinality of G. Okay, proof. This is fairly simple to see because stabilizer of u is a subgroup, step of u is subgroup of G. Okay, that implies order of step of u, stabilizer of u divides order of G. This is by Lagrange's theorem. Okay, now I wanted to prove that one. That one is the little tricky one. Okay, we have to understand the group action, what's going on. Let's understand the group action. First, G acting on power set of G. We will restrict this action to the step of u. What is step of u? Set of all G belongs to G such that Gu equal to u. How G acts on u? G small u such that u belongs to capital U. This is how it acts. So that means this step of u acting u as a element of p power u, it's like nothing, just a trivial action. But if you see the step of u acting is u as in the elements of u as, okay, elements of u as permutations. That means the step of u defines a group action in u. This is the idea. Now whenever we have a group action, remember that this is we always do. Let's take this is to be H. I am calling a stabilizer of u as H orbits. Okay, now we know order of u is nothing but order of H orbits. It's a virtue of the disjoint quality. This index runs over the different orbits. Remember that I claim each H orbits are same size as a set, as sets. Okay, let's see what is H orbit. Let A belongs to U. What is H orbit? The orbit of A, H orbit, H A, such that H belongs to H. In our action, this is H A such that H belongs to H. This is nothing but, okay, this is how it looks like. Okay, every element is looks like here. Now I am saying let OA, I am saying this is bijective with H, bijective. How? Let's define a map from here to here. Let's say F OA, H goes to HA. This is how. So we have seen, right? This is how this looks like. So it's okay. Well definedness is okay. You try to check. I wanted to check one to one. Onto is fairly clear because everything is here HA, and you take the same H. Onto is subjectivity is clear. Onto subjective both are same. Injectivity. Let's check injectivity. H1A equal to H2A. That is nothing but FA1. Sorry, FH1, FH2. Then look at this. H1A equal to H2A. Both sides I multiply by A inverse, so it will go H1 equal to H2. So that means F1 equal to F2 if and only if H1, this is well definedness combined with this well definedness, you check this is true. So it's 1 to 1, 1 to 1 and onto. Finally that means U becomes H orbits, that is summation of H only, that will be some number of orbits. So that implies order of H divides U. This is going to play a very crucial role, hence proved. Sorry for the outer noise. I couldn't able to control the outer noise. It is a little bit noisy here. Okay, so I think I finished the preparation. So we are going to use many group actions to prove Sylow's theorem one by